So far we've talked about modeling linear relationships, and this time we're going to talk about what if the relationship is not linear. So let's think about how do we check to see if the relationship is not linear. Remember that the data set we're working with is the Paris paintings data set with over 3,000 observations and 61 columns, where each row represents a painting. And for the time being, we're only working with a couple variables at a time. We're fitting a linear model, which assumes a linear relationship between our explanatory and response variables. But how do we assess this? One of the things we can do is look at a residuals plot, but let me backtrack for a second. I think that one of the first things you might do is just make a scatter plot of the two variables you're using in your model and check to see if there's a relationship between the two, like the width and the height of the painting, and if that relationship is linear. The thing is, sometimes slight deviations from this linearity might be hidden in a scatter plot, especially if you have lots of data and lots of scatter, and may not be as visible as if you're looking at a residuals plot. When we're looking at a residuals plot, and let's remind ourselves that a residual is the difference between the observed and the predicted values for each data point. So those are those vertical segments we saw on the scatter plots earlier. When you look at a residuals plot, we would like to see something like a completely random scatter around zero. And here in the residuals plot for the model that we've been working with, we're definitely not seeing that. We're seeing this kind of a V shape here. So let's first talk about how this plot was constructed, what is on both of the axes, and then we'll talk about what do we do with this information. So on the y-axis, we have residuals. So imagine that for every single data point, after fitting the model, we calculate the predicted values and we calculate the residuals, and then we plot those two new variables, the predicted values and the residuals. How do we do this? We know how to fit the model, starting with the linear regression function, setting an engine, and then defining our model fit. We save that model fit object, and then we augment it. So what augmenting basically does is for every single data point in our model, it calculates a variety of things for them. And two of those things is the fitted values, calls predicted values fitted, since it's after the model fit. So the fitted values and the residuals. It also reports the standard errors of the residuals, and we'll talk about those at a later time. So here I have a data frame with height and the width that I've used for my for building up my model. And then I have my column of fitted values. So that's plugging in the X values into our model and then figuring out what the Y hat for those observations are. And then the residual is basically calculated as the difference between the observed and the predicted or the fitted value. So that's a 10.3 here. Another thing I'd like to draw your attention to is that this augmented data frame has 3,135 rows, which is a little less than what we started with in our data frame. And that's we saw in an earlier video that when we actually plotted these data, there were some rows that about 250 or so of the rows that were being dropped because we had NAs in either the height or the width or both of those. So we're only able to fit the model to the records where we actually have data on both of these variables. So once we have this, what we can do is we have this data frame. The rest of it hopefully is a little bit more straightforward because we're just using a ggplot. On the x-axis, we have the fitted values, and on the y-axis, we have the residuals. And then one thing that's common to do is to put a dashed line at the zero. So just so to help your eye kind of figure out, are my residuals randomly distributed around zero, so we can see that dashed line around there. And the answer is no here, but let's next talk about what does that really mean. So here's another look at that augment function, just so we can see all of the variables that are calculated with it. As I said, for now, we're going to be focusing on the columns that are the fitted values and the residuals, and the rest we'll talk about a little bit later. So what we're looking for in a model, in a linear model, is residuals that are distributed randomly around zero, with no visible pattern around the X or Y axes. So this is what a random scatter would look like around, with no visible pattern along the X or Y axes. We're not looking for fan shapes. We are not looking for groups of patterns. We're not looking for residuals correlated with predicted values. So here you can see that as the predicted value increases, your residuals increase as well, and that's not something we want to see. We're really not looking for any patterns whatsoever. We want to see a complete random scatter. Why do we want to see a complete random scatter? Because what that would tell us is that after you fit the model, what's left behind, the residuals have no interesting pattern to them. Any sort of interesting relationships have already been captured by your model. And I'm saying interesting, but what I really mean is any sort of linear relationship has been captured by the model, and that was the only relationship apparent there. If there is still any sort of pattern remaining, what that tells us is that the linear model may not necessarily have been the best fit here. So what patterns does the residuals plot reveal that should make us question whether a linear model is a good fit for modeling the relationship between height and widths of paintings? This looks like that issue of the fan-shaped residuals. The variability of our residuals increases as the predicted values increases. So we can see that at the lower end, when the predicted values are lower, say between 0 to 20 inches or so, the residuals are quite condensed around 0. But then as the predicted values increase, how much we're off, so the variability of our residuals increases as well. So what do we do next? Let's try to explore linearity. Now the prices of our paintings are, we'll look at a new variable now, the prices of paintings. So our prices of our paintings are right skewed, okay? Very, very right skewed. And remember that the unit here for the prices is livres, so it's not euros, it's not dollars, it's not pounds. It's the numbers don't exactly translate to today's money, but still higher means more expensive. And here is the relationship between the price of the paintings and the width. So you might imagine, bigger the painting, the more it should cost. And it probably does a little bit, but if you've ever seen the Mona Lisa at the Louvre, it's pretty small actually. It's not a giant painting. So paintings, prices are not necessarily always highly correlated with their size. Maybe for certain types of paintings they might be, but for other types of paintings, especially if they're famous paintings, you wouldn't expect that to be the case. So we're not really seeing a linear relationship between these two variables here. What we're going to do is we're going to actually focus on paintings with widths less than 100 inches. That's about 2.54 meters. So that's really, really wide paintings we're looking at. So we're actually going to chop off our data for and work with paintings that are less than 100 inches. So here's where you can see on the left-hand side where you can see the plot for the prices versus the widths for those paintings. And then what you're seeing on the right-hand side is what if we were to take the log, the natural log of the prices, and then plotted that against the widths. We can see that there's more of a linear relationship in the plot with the natural log. And you're also seeing a lot of scatter. So you might be looking at this and thinking, is there really a linear relationship here? And maybe the question to ask is the relationship clearly nonlinear, or might it be linear? One of the a nice way of thinking about is their linear relationship is when you look at your scatter plot, think about not where the data is, but where the data isn't. To think about the negative spaces. And if you were to draw like these little triangles where we have the negative spaces, would we actually potentially be seeing a band of data, which might indicate that there may be a linear relationship? Here, what we're looking at is the same plots, except we're looking at residuals versus predicted values now. So not the price versus the width, but what if we fit a linear model to both of the data, in one case where the price is just in livres, and in the other case, it's the log of it. And then calculate the fitted values and the residuals, and then plot them against each other like we did earlier. So making use of something like the augment function. And in fact, the residuals that are on the logged model look a lot more like they're uncorrelated with predicted values. They're not showing that fan-shaped pattern to us. So it looks like by fitting a linear model, we were able to capture any of the interesting relationship, and what looks like is left behind looks a lot more like a random scatter. So we saw that price has right skewed distribution, and the relationship between price and the width of painting is nonlinear. That's what we observed early on. In these situations, a transformation applied to the response variable might actually be useful. So in order to decide which transformation to use, we should examine the distribution of the response variable generally. The extremely right skewed distribution suggests that a log transformation might be useful. And when I say log, I'm talking about the natural log. So in other mathematical contexts, you might see it as ln. But in most of statistics, and also in R as well, by default, the log function is the natural log. So here is that model where we have on the y-axis the log of the price of the paintings, and on the x-axis the width, and that purple line you're seeing in the middle is our linear model fit. How do we interpret the slope of this model? Well, let's take a look at these numbers. Here I've fit the model. So same as before, starting with a linear regression, setting my engine, and then calculating the log price and using that as my response variable versus my explanatory variable. And remember that I'm working with the Paris paintings data set still, but only for paintings that are less than 100 inches wide. And then ultimately I'm tidying up the model results so that they can be shown in the stable format to me. And really the two numbers I'm interested in are the intercept 4.67 and the slope 0.0192. But what do these numbers mean? So here's how I might write that model equation. The predicted log price, right? Not the price, but the predicted log price is 4.67 plus the slope 0.0192 times the width of the painting. So for each additional inch the painting is wider, the log price of the painting is expected to be higher on average by 0.0192 livres. What is the log price? What if you asked me how much does it cost to do something and I gave you the information in log pounds? That doesn't really make sense. So we use the logging to make our linear model work a little bit better in this situation. But then the interpretation becomes a little bit odd. It's not really a very useful statement the way it's phrased right now. So I want to remind you two properties of logs. When we subtract log A from log A minus log B, that's basically equivalent to saying log A over B. And then the other property is e to the log of x is basically x. It's kind of like they cancel each other out, right? So keeping these two in mind, we can undo the log transformation, if you will. So we use the log transformation to make the relationship between the two variables appear linear, then fit the linear model, check our model diagnostics with the residuals plot and say, well, these residuals look like they're randomly scattered around 0. Maybe I believe this model. Let's go ahead and interpret these coefficients. And when it comes to interpreting them, we are now stuck with that log and we're trying to undo that. And we're going to use these two properties for doing that. So the slope coefficient for the log transformed model is 0.0192, meaning the log price difference between paintings whose widths are 1 inch apart is predicted to be 0.0192 log livres. So if I was to put this in notation, really what the sentence that we want to really fill out is, for each additional inch the painting is wider, the price of the painting is expected to be something on average by a factor of something. So the first something is either higher or lower, and the second something is a numerical value that we want to get. So if I was to say that, think about two paintings, one with width x and the other one with width x plus 1. So two paintings, 1 inch apart. According to this model, if I know their log prices, or their prices, and then take the logs of these two numbers. The difference between those two is going to be our slope, 0.0192. So log of the price for width x plus 1 minus the log of the price for width x is 0.0192. Using the first property of the logs we reviewed, of log A minus log B being equal to log A over B, I can rewrite this equation as log of the ratio between the prices of paintings with width x plus 1 divided by x is 0.0192. And now I can use the second property and say I'm going to raise both of these, exponentiate both of these, right? And so what I get on the right-hand side is price for the, on the left-hand side is basically that ratio, the ratio of the prices for paintings that are an inch apart in their width. And then on the other side, e to the power of 0.0192 basically gets me 1.02, excuse me. So now we've gotten rid of the log. So what this is telling me is that for each additional inch, the painting is wider. The price of the painting is expected to be higher, right? On average by a factor of 1.02. It's higher because this is giving us a positive factor when we basically the ratio of these two prices of these two paintings is a positive number. So that's why we're saying it's higher on average by a factor of 1.02. Another way of saying this would be more expensive by 2% or something. So to recap, non-constant variance is one of the most common model violations. However, it's usually fixable by transforming the response, so the y variable. The most common transformation when the response variable is right skewed is the log transformation, so that's log of y, and it's especially useful when the response variable is extremely right skewed. This tends to happen with things like prices, for example. This transformation is also useful for what we call variance stabilization. So when the variance around your regression line is not stable across your entire plot, if you will, so you actually have this fan-shaped pattern, this transformation can also help with that as well. So when using a log transformation on the response variable, the interpretation of the slope changes. For each unit increase in x, y is expected to, on average, to be either higher or lower by a factor of e to the whatever the value of slope is. So that's our B1, our slope estimate. Another useful transformation is the square root, and that can be especially useful when the response variable is count. So should we be transforming or should we be learning more? These data transformations may also be useful when the relationship is nonlinear, but in those cases, a polynomial regression might actually be more appropriate. So in this course, we're going to be focusing on linear models. So something like a polynomial regression is a little bit beyond the scope of what we're going to be covering here. But what we've shown in this video is that if the linearity condition for your model does not hold and your residuals plot is showing divergences from what we want, that total random scatter of residuals around the zero line, but it kind of veers away from that from that in a particular way, especially in that fan-shaped pattern way. One remedy might be the log transformation, but other ways that other ways in which the linear model may not be a good fit for your data might actually require that you would fit a different type of regression as opposed to try to retrofit things into the linear model. You're welcome to try it for your final project though. So if you find that in the data that you have selected, there is this sort of nonlinear pattern and you're wanting to do some modeling with it, and the type of nonlinear pattern that you're seeing is not one that's necessarily helped with a log transformation or any other sort of transformation, and you'd like to try something else, I would be very happy to provide assistance for that, even though that's not part of the official curriculum for the course. A little aside, in some cases, when the value of the responsible might be 0, so and then you try to take the log of it, so log of 0 is not defined, And so you wouldn't be able to do that. A trick that's very commonly used is to add a very small number to the value of the response variable for these cases so that the log function can still be applied. So in this case, I've added a very, very small number. And what that's going to do is for any data where the observed value of the response variable was 0, you're going to add the small fudge factor, if you will, to all of them. And they'll all be kind of defined when the log is taken, but potentially kind of stay away from the rest of your data. It depends on how many of these you have and how far away they are from the rest of your data. In some cases, maybe they're not necessarily relevant to your analysis, but in other cases, this might allow you to kind of carry forward with your analysis without actually changing things a whole lot, because there's very little difference, if you think about it, between an observed 0 and an observed 0.00001 if the variable was a measured variable to begin with.